We're on the internet constantly, right? But you ever stop and think about what's physically making it all work? We're about to dive into the huge shift in data center design that really made our modern, hyper-connected world a reality.
I mean, think about it. Where does Netflix live? Where is your cloud storage? It's all in these massive data centers. And they're not just warehouses full of computers. No. They're more like sprawling digital cities that never, ever sleep.
And you know, for anyone lucky enough to actually step inside one, the sheer scale is just mind-blowing. This quote here really nails it. It feels like magic, like you're at Disneyland. It's the physical heartbeat of our digital world. So the big question is, how does it all stay connected?
Well, to really get a grip on where we are now, we've got to go back in time a bit. For a long time, data centers were all built using a very specific, kind of hierarchical blueprint.
Yeah, this was the go-to design for ages, the three-tier architecture. And look, it made sense. It was organized, it was logical, and for what it was designed for, it worked great. The whole idea was to split the network's job into three very clear, distinct layers.
So, what are these three tiers? Let's break it down. At the very bottom, you've got the access layer. You can think of these as the top-of-the-rack switches. This is where the servers actually plug in. From there, all that traffic flows up to the next level, the distribution layer, which is kind of like a traffic cop pulling everything together. And then, right at the top, you have the core layer. This is the big, powerful backbone of the whole network. Okay, this next part is absolutely critical to understanding everything that follows. This whole design, this three-tier pyramid, was built for one thing and one thing only, what we call north-south traffic. That's data moving from the outside world, you, on your laptop, into the data center to grab something from a server and then right back out to you.
But then, everything changed. A little thing called virtualization came along. And suddenly, applications weren't just living on a single physical server anymore. They were spread out, talking to each other across tons of different servers. And this kicked off a totally new kind of traffic, and a whole lot more of it.
So let's make sure we're crystal clear on the two types of traffic here. North-south is that classic user-to-server traffic we just talked about. But east-west traffic, that's all the chatter happening inside the data center, from server to server. It's the constant back and forth that modern, complex apps need to actually work. And look at this. This is what's so wild. That internal, server-to-server east-west traffic just exploded. Today we're talking about it making up something like 80% of all traffic inside a data center. The thing the old network was built for, suddenly it's only 20% of the picture. The whole game had changed. And, well, you can probably guess what happened next. This created a massive, massive problem. That old three-tier model? It was never designed for a world where 80% of the traffic was zipping back and forth between servers. In fact, it was basically the worst possible design for it. We were designing for a bottleneck.
I mean, just look at how inefficient this was. For one server to talk to another server just a few racks away, the data had to take this crazy long journey. It had to go from its access switch up to a distribution switch, all the way up to the core switch, and then all the way back down again through another distribution and access switch. It's like driving across town just to talk to your next-door neighbor. Absolutely insane.
So this led to some really big problems. First, all those hops added up to a ton of delay, or latency. And modern apps hate latency. Second, the paths the data took were unpredictable. And maybe worst of all, there was this safety feature called spanning tree protocol that would shut down extra links to prevent network loops. That sounds good, right? But it meant you had all this expensive cable and bandwidth just sitting there, totally wasted.
So the old way was officially broken. The industry had to basically scrap it and ask a really simple but profound question. How do we build a network that's actually fast and predictable for the way data moves today?
And the answer that came back was brilliant. A completely new way of thinking called spine leaf architecture. And let me tell you, this is the design that powers the internet as we know it. It's how the giants, think Google, Meta, you name it, build their massive data centers. And what's so cool about it is that the core idea is almost deceptively simple. You just get rid of one of those layers, flatten the network out, and then connect everything together in a full mesh. Okay, so here's how it works. You have two kinds of switches. The leaf switches, that's your access layer, where all the servers plug in. And then you have the spine switches, which act as the new super fast backbone. But the real magic, the secret sauce, is in how they're all wired together. And this is where the genius of it comes in, with a few very strict, very simple rules. Rule 1. Every single leaf switch connects to every single spine switch. No exceptions. But, and this is super important, Spine switches never connect to other spine switches, and leaf switches never connect to other leaf switches. And the servers, they only ever connect to the leaves. It creates this beautiful, clean, predictable fabric.
So you might be looking at that and thinking, wow, that looks like a mess of wires. But why is this design so much better? Well, the performance benefits are just staggering. It basically solves every single problem we had with the old 3-tier model. Okay, here it is, the #1 killer benefit. To get from any server to any other server in the whole data center, it takes a maximum of 2 hops. That's it. From the server to its leaf switch, up to a spine switch, and down to the destination leaf switch. Every single time. It's not just fast, it's incredibly predictable. You always know how long it's going to take.
This chart just lays it all out, side by side. The old way, variable hops, low predictability, wasted bandwidth, and a nightmare to scale. Spine leaf, a fixed 2-hop path, high predictability. Every bit of bandwidth gets used. And scaling up, it's so much simpler. You just add another spine and plug it in.
So how does it actually use all that bandwidth without causing problems? This is a little technical, but it's really cool. Spine leaf networks use layer 3 routing between all the switches, not the old layer 2 switching. Now, why does that matter? It means you can completely get rid of that old spanning tree protocol that was shutting down links. Every single cable is active all the time, spreading the load perfectly across the entire network. It's just so much more efficient.
So there you have it. Spine leaf came in and solved the huge speed and latency problem, creating this incredibly solid foundation, what network engineers call the underlay for the modern internet. Which of course leads to one final really exciting question. If this is the new foundation, this incredibly fast and reliable base, what amazing new technologies and automations, the overlay, are we now building on top of it?